So I'm excited to introduce Byron Booth, our speaker today from Georgia Tech. Byron did his PhD at Carnegie Mellon and then did a postdoc in the University of Washington. Byron is working in the intersection of robotics and machine learning, and his research tightly integrates both the theoretical foundation and actual system building. In the past, he worked a lot on spectral methods for learning predictive representations, and more recently has been working a lot on imitation learning, reinforcement learning, and today he'll talk to us about perception and control for autonomous driving, and I'll let Byron continue. Thanks for joining us.
All right, thanks a lot. Okay, so before I get started, I just want to mention that I spent several hours this morning like completely tearing apart the presentation and putting slides back in. So if there are problems following things or something doesn't quite look right, please stop me and ask questions. So I'm happy to take questions throughout the talk, and I'll try to adjust things in order to make sure it all finishes on time. Or maybe shut down questions if you guys keep moving, but feel free to ask me questions. All right, so I want to start out by considering this setup here. So this is a large number of KUKA robots, which are manufacturing vehicles. They're actually like BMW X series at the largest BMW plant in the world, which is actually here in the US in Spartanburg, South Carolina. It's a couple hours north of Georgia Tech. And one of the things you might notice here is that there's all these robots and there's this assembly line of vehicles, but you don't really see any people. So this is, a major engineering success. It shows that if you build robots which are large enough and heavy enough and powerful enough, you can precisely control those robots and control every aspect of their interaction with their environment. And when you do this, you can do amazing things like build all these vehicles almost completely autonomously. Now, in general, robotics has been very, very successful in manufacturing. But if you look a little bit more closely, so here we actually have a setup at Georgia Tech. If you look closely, the environment in both this picture and in the previous picture actually looks something like this, where there's cages around the robots, right? So if you look back here, you can sort of see these cages which are surrounding the robots and in each one of these modules. So, and despite their really impressive manufacturing success, the robots are not what I would call intelligent robots, right? They're autonomous, but maybe not intelligent. And this, of course, is not, or at least my vision of what robotics should be, right? So I want to free robots from their cages. I want them to be able to interact with a fluid, unstructured, chaotic, dynamic, and dangerous world like C-3PO or R2-D2. That's sort of what we think about when we think about like robots. Now, I don't think we're quite ready to build some like full-on C-3PO robot, but there's another robot from my childhood that is maybe currently within reach and contends with many of the interesting problems involving perception and control. So, of course, I'm talking about KIT from Knight Rider. So does anyone remember this? Yeah. Because like increasingly, it seems like the audiences are just like, I have no idea what you're talking about. So if you have no idea what I'm talking about, then you probably didn't grow up in the US in the 80s, and I feel moderately sorry for you. But to provide a little bit of context, Knight Rider was this TV show starring David Hasselhoff as Michael Knight, right? He was this high-tech modern crime fighter, and he was assisted by this robot KIT, which is an advanced, artificially intelligent, self-aware, and nearly indestructible car. So, just to show you some of the antics that KIT got up to, it liked to drive really fast and aggressively and jump through the air in order to get the bad guys and save Michael Knight. And these are capabilities that we don't really see yet on autonomous vehicles, despite all the progress which has been made. So you'll also notice that they seem to keep the landings a trade secret. They never quite show them. All right, so this leads us to today's subject. So our students basically built something like KIT at Georgia Tech minus the indestructible part, unfortunately, and it's only 1/5 scale. I'll talk about that in a moment. We call these autonomous vehicles rally cars. So I'm going to use rally cars as a vehicle to discuss some interesting problems at the intersection of machine learning and robotics. Yes, exactly. Okay, so so this is, like I said, a high-speed autonomous racing platform. It's a 1/5 scale truck. That's the basis for it. It's about 1 meter long. It weighs about 45 pounds, so it's about like this big. We've replaced all of the motors and everything, and the chassis and some other stuff. So it's got electric motors, a top speed of about 60 miles per hour. It has cameras, IMU, GPS, wheel speed sensors, and considerable onboard computational resources. So it has an Intel i7 processor, it has a desktop GPU, all on board, so we can do all the processing on board. So we actually control this vehicle with steering and throttle commands. A couple of our vehicles now have brakes, but we're not using them, so it's just steering and throttle. And by the way, I want to point out at this point that a lot of recent work in deep learning for driving only does steering. So this is kind of incredible to me. Like, throttle is pretty critical for driving fast, or you would imagine maybe just driving, right? You have to modulate the speed somehow. If you're thinking about racing, you need to go really fast on the straightaways. You need to go a little bit slower on the turns. So we have to actually reason about the speed of the vehicle, not just the steering angle. Now, unfortunately, we see in some of our experiments that throttle is actually much harder to master than steering angle. But I just wanted to throw out there that like these are the commands we're using in the car. Okay, so we have all this hardware for this intelligent car. Now the AI problem is, how do we learn or design, let's say, a policy that will control the car at high speeds over rough terrain and do this without crashing? And we're going to look at two approaches to this problem today. So the first approach is by any means necessary. We just want to get this thing to race really fast, maybe faster than our best human grad students can drive it. And then the second thing would be, can we do this using vision, which is, as we'll see, maybe a little bit more complicated. So we'll start out with this. So the first thing that I want to mention is that despite what some of my machine learning colleagues might tell you, engineering might be useful for robotics tasks. And in particular, a good approach to trying to solve a robotics problem like this might be to develop a pipeline where we take sensor data, we map it to some sort of perception module that maps to some kind of state estimation module, which then feeds into a planning module, and then we have control. And then, that executes some kind of action or motor torques or something like this. So this type of pipeline, where we unit test each one of these components and we use our prior knowledge about the problem, is what's recommended by systems engineering, and it has gotten us quite far so far in robotics. So this is, I think, a very natural way to kind of start this process of trying to get these cars to drive as fast as possible. So we are going to have a pipeline like this in at least the first part of the talk, and I just want to give you a little bit of information about what this looks like. So our perception is going to be based on differential GPS and IMU. This gives us accurate outdoor position information to within a few centimeters. We're also going to be using kind of standard state estimation techniques, which localizes the vehicle with respect to some map, which is given to the vehicle. So the map is computed from a GPS survey of the environment. We're going to assume some sort of system model, which allows us to predict what will happen when we apply different types of commands to the robot. I'll come back to that in a moment. And then using the system model, we're actually going to use model predictive control. And this is a control technique which allows us to optimize some short open loop control sequence, execute just a small portion of that sequence, and then re-optimize based on our current state estimate. So we have this kind of optimization heavy process which is going to be continually running on the car in order to choose good actions. Now, usually what we would do in model predictive control is we would actually write down a system model. So we would write down some model based on our knowledge of the physics of the car, and use that in order to predict what will happen when we execute some sequence of control. And the problem is that this can be quite difficult to do in practice. The assumption is that the interaction of the vehicle and its environment is precisely defined, but I want you to take a look at something. So what I'm about to show you is a slow motion video of the dynamics of our car as it's taking a turn at high speed. So this looks something like this. And so this is at quarter speed. You'll note that it's like bouncing and sliding and doing all sorts of crazy stuff. So it's the behavior which is actually very, very difficult for us to predict. It's difficult for us to write down the analytic model that captures this type of dynamics. And if you don't get the dynamics right and you feed those dynamics into the control system, then you end up seeing behavior which looks something like this, where the planning and control algorithms fail. And you can see that the car was oversteering here, and then the grad students, you can kind of hear them gasping / screaming in the background when their car crashes, because that means they have to rebuild it. So yeah, and we have a lot of video like this. So yeah.
So how sensitive the MPC, model predictive control, to changes in the car? So if I let's say I add another battery, so I added another few pounds to the car. Now I have to rewrite my model.
So it depends on how fast the car is going, for example, and what sort of surface it's on. So yeah, if you add significant weight to the vehicle or you change the surface significantly, then the dynamics change. And this is something which you would have to deal with. So I'll talk about this a little bit more maybe in the future work section. So right now we're going to assume that like the weight on the car is going to be about the same. But this is something that you want to be able to deal with in practice. Okay. All right, so kind of going back to our previous thought about physics and engineering being useful, maybe a more accurate statement would be, well, they are useful, but they also make simplifications and assumptions that might not be accurate, and this can be dangerous. So the first thing I want to mention is that even though that's true, this still works for well-behaved driving. Okay, so if you're driving at like a reasonable speed on a reasonable surface, then you can write down nice analytic physics-based models which tell you about the behavior of the vehicle. But of course, what we want to do is control the car when it's doing stuff like this, and so we want KIT. We want it to misbehave in some sense. Okay. So let me talk a little bit about model predictive control. So this actually has a long history of successful applications, both in doing things like controlling chemical plants to being used in aerospace engineering. But most methods are geared towards linear quadratic systems with convex constraints. And in our situation, we have very nonlinear dynamics and non-convex costs and constraints. So sort of the standard tools will not necessarily work well. We also usually use a physics-based model of some sort, and this can be hard to specify in our case. So remember the car kind of coming around that turn and jumping off the ground or just being on two wheels. And so, a natural question from someone like me, who's a machine learning person at heart, is, well, maybe we can actually learn a dynamics model and generate some sort of MPC algorithm which still works well. Now the problem is that MPC is often formulated for control affine dynamics. So these are dynamics models which have certain types of restrictions. And we would actually like to use a very general function approximator in order to model our dynamics. So you can imagine something like a neural network or a Gaussian process, something like this. So in order to do this, you need to come up with a new model predictive control algorithm which can actually take models like this. And what we did is we came up with a new approach. And this was finalist for best paper at ICRA this year. I'm not going to go too much into details, but I will give you an overview of how this algorithm works. And I'm going to be focusing a little bit more on actually learning the dynamics and some of the challenges. Okay, so we came up with a model called Model Predictive Path Integral Control. It's a stochastic optimal control method which works by forward sampling trajectories. So each trajectory, we use our dynamics model, we roll out trajectories along with random perturbations to the optimal controls. So this basically creates like a spray of trajectories. It's illustrated something like this. I'll actually show you what it looks like on the vehicle in a moment. And these trajectories allow the algorithm to basically evaluate many possible control sequences and look at the cost along the trajectories. So what we end up doing is we end up computing a weighted average of these trajectories, which we weight according to their desirability. So this has something to do with kind of integrating the cost among them. And this gives us a smooth, low-cost trajectory. We can then execute the first control in this trajectory, and then repeat the process after updating state, basically using the previous trajectory as a warm start. Okay, so does this sort of make sense? Like at each instant in time, we're creating this whole set of trajectories. There's actually several hundred of them, and then evaluating them and choosing an action. So this ends up being a very, very fast process if you have a GPU, because you can use all of these different cores to be rolling out trajectories simultaneously. And in fact, we execute about 5 million predictions per second on board our car with just a, what is it? It's a GTX 980 GPU. So this is really fast and it can be run in real time. Okay.
Question.
Yeah.
So you say it's really fast, which is great. As much as I enjoy the idea of flying over traffic on I-85 in a car that knows how to do that, what if you're driving on I-85 and they don't salt the roads and it ices over and there are only patches of ice? And so most of the time you're driving straight and fine on regular road, but then you hit a patch. Is your model fast enough to account for that sudden change in terrain?
Yeah, so that's a great question. So there's an interesting engineering challenge. So first, there's a couple components that you have to think about. So first of all, you want really good state estimation. So at each instant in time, you want to be able to know where your car is and maybe the various accelerations on your car, right? So maybe you want to know whether you're slipping or not, things like this. So having a good state estimator is critical. This allows you to very rapidly adapt in the sense that you're updating your situation and then you want to maybe roll out new trajectories from that. The second thing is you want to have a dynamics model which is maybe sufficient to capture what happens when you're in these kind of icy situations.
Have a separate model for ice itself rather than like.
Yeah. So we haven't done this, so I don't know exactly what would work. But one thing which might be reasonable is to have multiple models and think about either switching between them or having some kind of ensemble. So there's a lot of interesting possible future work on how do you deal with rapidly changing environments? How do you update your models to be able to handle that? How do you switch between models? This is true not just, of course, for ice, but if you change from one type of surface to another, just in general, right? So you're on a dirt track versus you're on grass versus asphalt, something like this. So these are really interesting questions, something we haven't completely nailed yet, but it's definitely future work. Yeah.
So when you sample trajectory, so you're at XT, you're observing the environment, and you're starting to sample. You branch out only at the start position, or you start and slowly branch out more and more?
Right, so in this case, we're assuming that we know the state of the vehicle. It's actually a little bit complicated how it works. The environment itself is in the cost function. And this is something we can talk about maybe more offline, but we have a very low dimensional state for the vehicle. It's actually about 4 dimensions. I think it's horizontal let's see, forward and lateral velocities, roll, and heading angle, things like this. Then we have our dynamics model, which takes this 4-dimensional state plus steering and throttle. I'll talk about this in a moment, and maps that forward to accelerations. We use this in order to roll out our trajectories. Those trajectories are evaluated based on where we are. So we assume that we know our state, right? So we assume that that's like that we're certain about it.
So state is like position.
Yeah. So we're currently we have a state estimator which has some distribution over state, but for the controller we take our map estimate of the state, and this is, again, going to be these sorts of this information about the various velocities and heading angle, things like this in the car. Then when we roll out trajectories, we're actually comparing those trajectories to the environment in order to generate the cost of each of those trajectories. So basically what we're saying is we want trajectories which kind of keep us near the center of the track, allow us to go as fast as possible, minimize control authority, like things like this.
And then you do a weighted average.
Yeah, we do a weighted average over these trajectories based on cost in order to find a trajectory which is it's an average trajectory which has low accumulated cost, and then we execute like the first few actions of that, and then we repeat this process. And the whole thing is executed at about 10 hertz in order to do like the replanning. So our state estimator is actually going at about 200 hertz, and then we're generating new actions at about 10 hertz.
What are the typical magnitude of the number of trajectories that you generate?
Yeah, so somewhere in the order of 600 to 2,000 at each point in time. Yeah.
I don't mean to keep you in the weeds on this slide. I just think it's really interesting. You're saying you're running your model update at 10 hertz, so you're basically new control.
Right.
Have you looked into what is the thing that's keeping you at 10 hertz? Is it the 5 million evaluated trajectories, or is there something else in this that's sort of the speed limiter of that control loop update?
No, it's generally actually generating and evaluating those trajectories, and that has to do with how many trajectories you have, although that has to do with how many cores you have on your GPU, like how many you can evaluate in parallel. And so the second thing is how long those trajectories are. So we have to think about, how far in the future do I need to look in order to control this car reasonably well. Honestly, at this point, this is something which is hand-tuned, right?
Yeah, I bet you there's a ton of really interesting questions.
Right, but in general, we're looking at, like 1 to 2 seconds in the future when we roll out these trajectories. And that's reasonable. I think somewhere in the 3-second range is kind of what you would want in general on a vehicle. So, but that's what we're doing.
Thank you.
Yep. Okay, cool. So the next thing I want to talk about is where do we get this dynamics model from? One of the really interesting problems here is how do we actually learn a good function approximator for these dynamics? And we make a few assumptions here. So first of all, we assume that the car is exhibiting general, discrete time, nonlinear dynamics. We also do things like partition the state into its configuration and time derivative. This is standard in controls. And then we attempt to learn, in our case, a fully connected neural network, which basically maps the current state to observed accelerations. So once we have this fully connected network here, we can integrate forward in order to make predictions about the future. Now, one of the things which is interesting is that this problem of actually just learning a neural network model ends up being not so straightforward. So remember that our goal was to learn this function, which is, we're going to think about this neural network as a function f, parameterized by theta. So this is just the weights in the neural network. And it's mapping our state and control to observed acceleration. So the first thing we do is we collect data from a human teleoperating the car around the track, right? So we need to get this data from somewhere. Now, if you treat learning dynamics as just like a naive supervised learning problem, you'd see an objective function, which looks like what I've written up here. And this objective function basically says two things. So first of all, I'm trying to minimize my prediction error. This is kind of the normal thing that you would see. But the second thing is, if I just take my data and treat this as a supervised learning problem, then the expectation that I'm computing here, right, this thing I'm trying to actually minimize, depends on the distribution of data which was induced by the exploration policy. Okay? So the problem is that once I learn these dynamics, small errors in the learned function will actually accumulate as MPC uses this function in order to execute control. So basically what happens is this results in a trajectory which starts to stray from the demonstrated trajectories. And the problem here is that if the trajectory strays too far, you start to enter into some area of the state action space where you have not observed data. It's actually a little bit more complicated than this because we're actually talking about like, various velocities and things like this in the car, not just location. So if the policy strays too far, the car starts to experience these dynamics which it's never encountered before. This causes errors to accumulate even faster, and then really bad things happen. And so there's actually a name for what this is. So this is an instance of a problem called Covariate Shift, where there's a mismatch between the training distribution of data and the test distribution. And this is actually extremely common in autonomous systems where robots are operating in closed loop with their environment. So fundamentally, this problem can be viewed as one where we specified the wrong objective function. So rather than computing the expectation with respect to the distribution induced by the exploration policy, what we should have done is we should have computed the expectation with respect to the distribution induced by the policy that actually uses the learned dynamics. Now, unfortunately, optimizing this is really hard because you can see that the distribution, it's generated by this function which depends on our parameters. So there's actually parameters like in here in this expectation in the in this distribution which is being generated. So it's quite a nasty optimization problem. I know someone must have a question at this point about this. Does this make sense? So rather than I have to think about how this is going to change based on how I change the parameters themselves, and they're buried like in this expectation. Yeah.
So I would see that like the P-Explorer, that's like using your past data to set an expectation, and
Correct.
the P data you're using like your current data set to have that expectation. But
Yeah. So you want to minimize this loss given the data which is generated by the function that you're trying to approximate.
right, so you don't know like what that expectation would be, or you would use.
Yeah, or like expectation. So there's like kind of the parameters that you're trying to optimize here are also like kind of inside the expectation in this distribution which is being generated. So it's complicated. Yeah.
I mean, so what would be the difference here? Because I guess you're trying to estimate P theta using you're given P Explorer. I mean, you're trying to estimate P theta now. So it's like you don't know. I guess as we've seen, you don't know. Like I guess what you don't know. You don't know that path. You never explored.
Right, exactly. So that's the challenge, right? So like now you actually want to evaluate this function in kind of all the areas of the state action space that your optimized function will end up being in, not just where it was when the human like provided the initial data. Yeah.
I mean, what would prevent? I mean, the problem it seems like with this objective is that your policy or this theta could degenerate into something like this going forward, where it's very easy to predict and minimize your error.
Right.
But it wouldn't help you.
So the thing which kind of prevents that is the fact that the dynamics here are being handed to this optimal control algorithm, which is trying to minimize its own objective, right? It's trying to say, go as fast as possible. And while it's doing that, right, while it's minimizing this other objective, it's generating new data that this needs to be able to like predict well. So we'll actually talk about that explicitly on the next slide.
So,
yeah, 2 more questions.
naive question. I mean, is this something that could be resolved by having worse training data?
Yes, so if you have enough data from like all areas of the state action space, then this is not really an issue anymore.
Right.
But you don't necessarily want to randomly like move this car all over the place in order to collect data, because that might
you can have
result in lots of
children
crashes and things.
Run the court, like there's like lower level expertise that gets you more.
The other thing is we actually want to drive this thing faster than the human, so we ultimately want to be able to collect data that we don't even know how to generate yet, right? And one more question, and then I'm gonna.
So the objective of the controller is inside. Basically, to drive this learning is to drive as fast as possible.
Yeah.
So But there is also the objective of actually following the path. Or you mean, or you say that.
So the optimal controller is trying to basically follow the path, drive as fast as possible, minimize the amount of steering angle and throttle which are applied to the car. It's trying to do these things. And that optimal controller is taking my dynamics function as input and kind of generating data in some sense that you need to minimize this from this objective for.
So this is these parameters you just mentioned. This is what you use to compute the costs of the different trajectories that you're rolling out.
Right. So the MPC algorithm is trying to compute the costs of all these different trajectories, and then it's choosing some action. But in order to compute those costs, it's using my learned model. When it uses that learned model and ultimately chooses an action, that generates a new data point, basically, that this should have, been able to predict well. So maybe this will make sense by kind of looking at this a little bit more detail. So you can actually view this as a game. You can think about it as a two-player game where basically player one takes samples from the system and learns a dynamics model. That model is then handed to the controller, which uses the learned dynamics model to try to optimize its objective, right? Like driving fast, not crashing. So the control system can literally be thought of as probing this model for exploitable errors. It's trying to exploit the dynamics in order to minimize its own cost function. And as it does this, it generates new data which can be used to evaluate the accuracy of the learner. The learner then takes the new data, updates its dynamics model in order to try to be more accurate, and then this process can be repeated. So this kind of tells us how we can start to get at solving this problem. So another way of thinking about this is through online learning. So effectively, what we end up doing in order to learn a good dynamics model is that we fix the distribution at each iteration and then solve a supervised learning problem. So the training process will kind of proceed as follows. So we first collect data from a human driving the rally car around the track. We collect new input-output pairs for the dynamics function. And then, so this is like the state and control input to acceleration. And then we add these to some existing data set. So this starts out being empty. So when the human teleoperates the car, we populate this data set. We then retrain our dynamics model based on this data. We attempt our task with our model predictive controller. Here's the first time you can actually see what this set of trajectories looks like for the car. It's a little bit dark, but and what this does is this is now executing the model and producing more data that we can look at. So given this new data, and we add that to our data set, we now retrain the model on the larger data set, hand that to the MPPI algorithm, and then repeat the process over and over again. And what this does is it results in a more robust dynamics model that we can use in our policy to actually drive the car fast. And in fact, what we do in practice is we start out with our exploration policy. We try to run our MPPI algorithm at like a reasonable speed. And then at each iteration, we slowly basically increase the speed. So we change the cost function on the MPPI algorithm so that it tries to drive the car faster and faster. And as it does that, it gradually builds up this database of data, which can be used to retrain the model and get the car to actually drive really fast. Yeah.
Now, just a quick question.
Yeah, sure.
So you're learning this for a single track, right? The moment you go to another track, dynamics model and everything deployed?
So right now we're learning this for a single track, like what I've presented so far. You can actually learn the model on one track and put it on a different track, and we have done this, and I'll show you some results for that a little bit later. So one of the main things to think about is that these dynamics models are, so first of all, it actually has to deal with changing dynamics every time the car goes around the track, right? So the surface is changing, and the car is in sort of different dynamic situations every single time. So it already has to do pretty well in kind of being able to generalize. The second thing is, yeah, there's an interesting question. If I learn dynamics on this track, does it actually transfer to, you know, a new environment which is, let's say, sufficiently similar? The answer to that is yes. So we have done that test, and I'll show you a video of it a bit later. Yeah.
So this loop, how fast is this retraining running?
So total training, like clock time for basically training up the car, is about 20 minutes on the track. We end up generally doing somewhere between 3 and 6 iterations of this. So we collect like 3 to 6 mini batches, which consist of several laps around the track.
Okay. And is this something that once the car is running, is this something that you then turn off the online learning, or is it always going around, and is it fast enough to keep doing it, or can you run it in the background? And once it's good enough, it like keeps going, but it's just always in the background getting a little bit better.
Yeah, so currently we turn it off, but that's exactly what we would like to do. And in fact, we don't want to just kind of be doing this with sort of fixed mini batches where we run it, but we want it to be doing this like online all the time as it changes surfaces and things like this. This is ultimately what we want. We haven't gotten it yet, but you know, it takes time.
And then one very quick,
yeah.
How deep is that network? Like that?
It's very small actually. So I'll show you in a minute, but it's basically a 2-layer neural network. Has somewhere in the order of like 1,000 neurons.
Okay, awesome. Thank you.
Yeah.
I was just thinking, because you have to do everything like in real time, is there any room for like running a simulation a bunch of times to gather more data for all the different sort of dynamics that?
Yeah, so the thing which is problematic with that is it's really hard to actually characterize the type of dynamics that we see on this vehicle using a normal simulator. So we actually have access to quite a good simulator through mechanical engineering, doing some work with autonomous driving. But when we're driving at like these relatively high speeds, it's high speed for a little car, the type of dynamics that we encounter are just not modeled well. So if I'm driving this car at maybe like 5 meters per second, I can use a pretty good off-the-shelf dynamics model, in which case I could potentially leverage that in order to collect more data, and I can vary some things. But once I'm starting to get up near like the 8 to 10 meters a second on this track, the dynamics get so crazy that those models are not even like at all helpful. So we were looking at things like, how do I model the residual, right? Like, how do I try to use this information that I have in order to do well? It turns out that at like the higher speeds, it's like not even worth doing. I'm happy to talk more about that later. Yeah, one more question. Yeah.
The control decision is made based on the dynamic of the car. For example, the surface and the angle.
So we have our current state, and then we're using our learned model to.
And it also depends on the map, the position of the car. Right?
Correct.
So if we train the model on this track and we change to another track,
we have to give it the new map.
Changed.
That's right. So basically, you have to update the cost function for MPPI. So for the controller, which the cost function actually includes the map. Again, I can talk about that more later maybe. But you have to give it the new cost function. But we can keep the dynamics model the same, and it still does reasonably well on like the new dirt track. So these are sort of separate things. You can think about trying to model just the dynamics of a car going fast versus the cost function, which is actually used in order to determine precisely how I should turn in order to stay on the track. Okay, so let's actually take a look at some results. So here's the neural network configuration. Quite simple, actually. So Paul, one of the grad students, is driving the car around this track. He's actually been driving these cars for about 10 years. And he's pretty good, but you know, the car starts sliding a lot in the turns, so it's quite difficult for the human to control them, so you can see it slowing down. But this is basically generating our exploration distribution. Then we run about 5 iterations of the approach, which I talked about. And we can get the car to drive consistently faster than Paul. So we'll beat him on every lap around this track, and it's very robust. You can see here are the rollouts using our learned model. You can see them here. This is just an onboard view from the camera, although we're not using the camera in this case to control the vehicle. Okay. Yeah.
So is there a fundamental difference between doing this and just getting a real rally car? I mean, just make everything bigger?
Well, so we can crash this and it's not so like catastrophic.
Yeah, I mean, except magnitude of everything, cost.
Yeah. And like, speed and all this kind of stuff. So, so that's an interesting question. So there's some people at Stanford who are doing pretty interesting work trying to do autonomous racing on racetracks with like race cars, right? So they're going about 130 miles an hour with these vehicles. But in some sense, their problem is easier. Right, so it's harder in many ways in terms of like engineering and like keeping this car from breaking and all that kind of stuff. But the control problem is not quite as difficult because the interaction with the track is actually fairly well understood, and they can precisely model things like how tire pressure affects the vehicle. We can't do that here. Those
because
types of
the
models. Yeah, like this surface is significantly harder to actually model. So let me just show you I just want to show you some robustness things here. So here the car is coming around the track. This is using our learned algorithms, coming around the track. You can see it hit this object, this little rock, which knocks the back of the car out of alignment, but it's able to actually recover from this just fine. And that has to do with the fast state estimation and the fact that we're extremely rapidly able to update our plan using MPC. In general, we have like hours of this video to watch it for a long time. I think it's very cool. But you can see that the car is robust to fairly complicated dynamics. It's sometimes completely off the ground. It's often in a slide on the side. It's sometimes on one or two wheels, but it's able to robustly run. So we can literally just keep running it until our batteries run out.
You said you wanted to go. Oh.
No, go ahead.
Oh.
Yeah.
You said you wanted it to go faster than a person. So did you learn any particular patterns of driving that humans don't do, but your robot somehow managed to pick up?
Yeah, so the car has learned to power slide through turns, which the human is not so good at. So it can actually keep the car at high speed while sliding sideways through the turn. And it understands that well enough, like it can predict that behavior well enough that it's able to consistently do that on like every turn. And that's something which is hard for a human to master. And there's a couple reasons for that. The reasons why it's hard for the human, including, well, we're actually not on board the thing, feeling the forces, seeing what the car can see, like this sort of thing. We have to look at it at a distance and be able to try to control it. So this is something which is just hard for us. So all of the advantage basically is by going faster through the turn.
Now, what about the case where you had the squiggly turn? Here you have a bunch of very simple turn left situations, but in the diagram you've been shown, you had one case where it's clearly bent track.
Yeah.
Go straight through, or?
Yeah. So we can handle those situations as well. With this car, part of the issue was actually getting Georgia Tech to give us space for a track that was reasonable size. So as of this last fall, we now have a track which is fairly complicated. I'll show you a video of it later. So you can learn dynamics on this track, and then you can put the car on the other track, which has both left and right turns and longer straightaways, tighter turns, things like this. So I'll show you that. Okay. All right, I better keep moving because I'm already starting to run out of time. All right, so basically what we've done is we've been able to get this car to run really fast, faster than our human expert can drive it, and we've done this kind of by any means necessary. Now, the question which is interesting to me from a robotics AI standpoint is, how do I actually do this with just like visual input? It's 2018 and computer vision is dominated by deep learning, so of course we should try that. So basically what we want to do here is attempt to learn a deep neural network policy that maps images and wheel speeds directly to steering and throttle commands somehow. And then we want to train this end-to-end somehow. All right. So it would be pretty cool if this worked. But let's think about what this means. So at its essence, this is basically a reinforcement learning problem. So the goal is to directly find a policy parameterized by theta that maps states or maybe observations to actions. And we have an objective, which looks something like this. So our objective is to find an optimal set of parameters that minimizes accumulated cost. And note that when we're looking at this, this objective, it looks kind of similar to one of our previous objectives. You have this distribution of trajectories, which is now induced by our policy, the policy that we're trying to learn. The cost terms here are, again, these are instantaneous costs, which in our case basically say that driving slowly is bad, crashing is bad, lots of actuation is bad, like all these sorts of things. So we can think about this problem as basically a policy iteration problem, which is an interactive process. So again, what we're going to do is we're going to initialize a policy, we're going to execute the policy and evaluate it somehow, evaluate the expected cost to go, and then we're going to use that to update the policy. So in order to do this, I want to describe a procedure which will become maybe a little bit more important later, that we call roll-in, roll-out. So the idea is that in roll-in, we execute our current policy from some initial state. We then sample a state under this distribution. We then sample some action A at this state S and execute it in order to get our next state S prime. And then we're interested in whether this sampled action is an improvement over the expected action in our policy or not. And so in order to find this out, we end up rolling out under our current policy again, and then we use this rollout to evaluate future costs that we encountered after taking action A. So if we sum over all of the costs, the costs in all of the steps in this circle, which I just outlined in purple, we get an estimate of the state action cost to go, which we call Q. And then what we want to do is we want to adjust the parameters of our policy to increase the probability of actions that result in low cost to go. So this is pretty basic reinforcement learning policy gradient stuff. We're trying to essentially compute a gradient of the accumulated cost with respect to the policy parameters that allows us to incrementally update these parameters. And again, the Q function here is the expected cost to go of the policy pi given the current state in action. And then the idea is just that moving in the direction of the policy gradient updates the parameters of the neural network policy to increase the log likelihood of actions which result in low cost to go. All right, so another way of thinking about this is that basically this is trial and error. We're trying to improve our policy by randomly sampling actions and kind of seeing what the effect of those actions are. The problem is that it requires a huge number of interactions with the system in order to learn good policy parameters. Now, I just want to mention that this works for games and simulated tasks and things like this. So, at Google, you can send out tens of thousands of jobs in parallel to train agents. And you can actually train the agents to learn to do all sorts of amazing things like beat world champion players at Go and stuff like this. So it's super cool for these sorts of tasks, but I care about learning on robots, and we don't have the luxury of millions of interactions and a continuous supply of agents that we can run and destroy, right? So it takes time to collect data on a real system, unlike simulation. The cost of mistakes is very real. So a partially optimized policy is dangerous to both the robot and to people around it. And when the robot makes a mistake, we have to purchase new hardware, we have to rebuild the robot. This can take months of grad student time and thousands of dollars. So doing the standard RL type stuff is not great for us. So in summary, although reinforcement learning is in some sense the perfect framework for trying to understand the problem of learning policies, which, for example, map images to actions, reinforcement learning algorithms are generally fairly impractical for these types of tasks. So what's an alternative to this? So one alternative is that I can somehow try to leverage expert guidance to do a better job. So what I'm going to do is I'm actually going to skip a few slides because I'm short on time. But there's some sort of simple ways of doing this. Okay. So what we're going to do is we're going to think about the problem of imitation learning. We want or to learn a policy which imitates some expert. And we're going to think about this kind of from a reinforcement learning-like perspective. So we're going to view imitation learning as an interactive process again, where we initialize some policy, we then execute the policy and evaluate feedback on its performance. In this case, the feedback is going to come in the form of an expert, and then we're going to update the policy. In particular, I'm going to tell you about this algorithm called aggravated, which just means aggregate values to imitate. The D has to do with the fact that it's differentiable, but yeah. Okay, so again, in this case, we're going to use a roll-in, roll-out procedure. So again, we're going to roll in with the learner's policy. We're going to terminate at some state S. We're going to sample some action in order to get to S prime. So everything is basically the same as before. But now we want to ask the following question. We want to know whether this action is an improvement over the expected action in the expert's policy. Like how does this action relate to what the expert might do? And in order to get this, what we're going to do is we're going to actually roll out under the expert's policy. So here we roll in under our own policy, we choose some action, and then we see what the expert does from that state. And what we're then going to do is estimate the expert's cost to go. So just in summary, what we're doing is we want to adjust the policy parameters to increase the log likelihood of actions that result in low cost to go with respect to the expert. Another way of thinking about this is we want to evaluate actions in response to like whether the expert can do well after we take that action or not. So for example, if I'm driving along a highway and I'm like in the middle of a road, and the expert says, you know, turn the steering wheel a little bit, and I don't. I turn the steering wheel maybe slightly away from what the expert suggests. If there's no cars around and I'm in this kind of nice situation, and I hand the car back to the expert's not going to really get any sort of, like the expert can easily recover. Okay? If I do the same thing, but I'm driving along the edge of a cliff, and I slightly deviate from the expert's action and I drive off the cliff, this is a situation which an expert can't recover from and seems significantly worse. So basically by evaluating the expert's cost to go, we're trying to match, we're trying to learn a policy which matches the expert's accumulated cost or reward as opposed to directly just matching the expert's actions. Okay. So this results in an algorithm which uses this roll-in, roll-out procedure. So this is what we call aggravated. We basically roll in under our policy, roll out under the expert's policy, and collect a new batch of data. We estimate a cost-sensitive loss on this batch of data, and then we generate a gradient descent type update based on this loss, and then generate new data. And then we repeat this process over and over again. Yeah.
In practice, how long do you have to roll out afterward to estimate the cost to go?
Yeah, so that's a great question. So hopefully not very long, because it becomes sample inefficient to basically roll in under my own policy and then have to hand off to the expert.
Yeah, each time you get a single update.
Right, so there's kind of two things you can do to try to overcome this. Roll out for only a very short or maybe just a single step. So you just look at what did the expert do versus what did I suggest, and use that to update the cost. Or sometimes the expert can just hand you a value function for any state. And this is an interesting case, which I'll come back to in a moment. If the expert is not human, the expert might actually have access to a value function which it can give you directly. Okay. So one thing I just want to show really quickly. This approach is similar to policy gradient approaches from reinforcement learning. So here we think about this as like an imitation learning policy gradient. Basically what we're doing is we are using the expert's cost to go, and we try to improve our policy by taking a sequence of gradient steps towards the expert's policy. So if you just look at like RL policy gradient, really the only difference is that we use the expert's cost to go instead of the cost to go for our current policy. So this allows us to very quickly converge to the expert policy with very few interactions in the environment versus a policy gradient which has to execute many trial and error steps in order to converge to a good policy.
When you say expert policy, is that the policy that's using all available means, or is that an actual human?
So I'm just going to think of an expert as some sort of oracle. That expert could be a human, it could be another algorithm, it could be something with more resources, either computational resources or sensing resources than what we actually have on our current system. So I'm just going to say that there's, some sort of oracle who can provide us information about either what action you should execute or kind of what the cost to go is if you execute a particular action. Okay, I'll talk about what we do in a moment. So the fact that this imitation learning algorithm is a lot like policy gradient means that there's lots of different implementation options. So we can do like a TRPO version, a PPO version, actor critic, generalized advantage estimation. We can leverage all of these different types of tools in order to do imitation learning. Okay, so I just want to briefly mention that we can actually say some interesting things about the performance of this algorithm. So first of all, we can ask, is imitation learning actually better than reinforcement learning? Can we prove anything about this? And it turns out that you can. So there exist MDPs for which imitation learning requires exponentially fewer samples than reinforcement learning in order to get the same performance. And for general MDPs, imitation learning requires polynomially fewer samples than RL. So this is something that you might imagine is kind of obvious, that imitation learning should allow you to learn faster, but we can prove it. We might ask, does this approach actually converge? So the answer is no. So unlike reinforcement learning, our imitation learning policy gradients don't necessarily converge. So we actually provided the first counterexample showing that it doesn't converge. And then we also characterized what you need in order to ensure convergence. So you need stability, which basically means that small changes in the policy must result in small changes in the state distribution in order for these types of approaches to converge. Then there's a question, how do we actually estimate this experts Q function in practice? There's some kind of interesting ways of doing this approximately. You can get this Q function for free sometimes if your expert is actually another MPC algorithm. If the expert performance is stable, you can estimate an upper bound, which works well in practice. And then finally, you might ask, can I combine imitation learning with, like, let's say, a suboptimal expert with reinforcement learning in order to improve over the expert? And the answer is yes, and we have some papers which are accepted and in submission, which talk about that. All right, so let's get back to racing. So we wanted to train this deep neural network. And what we want to do is basically update these parameters somehow end to end. We're going to do this with imitation learning. So we're going to think about experts. So what kind of experts are available during training? Well, we have a human who can drive the car. But the other thing which is pretty cool is that we actually have an algorithm or system with more resources that we can use to train the neural network, which is what I talked about in like the first 2/3 of the talk. Right? So this algorithm tells me how I should act in every state. And I can use that to train my deep neural network. So the overall system looks something like this. I have a learner, which is trying to map camera and wheel speed sensors to some kind of low-level controls for the car. And then I also have an expert, which is using an IMU and GPS in order to do state estimation. It has a learned dynamics model, and it has its own cost function, and it's using this to basically tell the learner how it should be acting at each point in time. And then finally, there's some safety stuff that we don't really need to talk about, but are actually important in practice. Okay, so just in general, we can do high-speed autonomous driving using these low-cost onboard sensors without any sort of state estimation, planning, map, anything like that. It's directly mapping the images to actions. And here you can see the result of the model predictive control expert, which is just using GPS and IMU, but is able to run very, very fast and is pretty good. saw in the beginning. And then here's the learn policy, which is literally using these images and wheel speeds in order to choose how to act as it's going around the track. And you'll note that it is more or less running at the same speed. It's a little bit complicated because it's kind of ends up in slightly different areas of the track each time, so it has to be able to generalize reasonably well, but it works.
So the input on the right, that's the input to the network.
Correct, and wheel speeds.
To clean the lens.
Yeah, well, that's something that we actually want to be fairly robust to that sort of stuff because, especially when there's multiple cars. Okay, all right. So that's it for the main content. I want to tell you about a few of the things which are kind of ongoing and that we're looking at. So first of all, there's some question about, does the rally car basically only turn left? Oops, does this not want to run? There we go. Okay, so here's our new test track, which, as you can see, is not just a nice ellipse, but is fairly complicated. This car here is using the algorithm that I talked about in the first part of the talk. It's using learned dynamics from the old track. So we basically trained it going both directions on the old track and are now using it to control this car. And we're pretty excited about this new track, but we've just started using it. So it got built last fall and it's kind of just coming online. Okay. We talked a little bit earlier about how we want to use fast online updates to the policy as conditions change. So actually what's happening here is in the wintertime in Georgia, it's generally pretty nice out, but in the morning the track is maybe frozen, and by midday it melts and the dynamics radically change. Also the vehicle itself changes due to this. We currently have 3 rally cars. We're building 3 more. So here's the lab where they're being built. The 3 in the kind of front are the ones which are currently operational, and the ones in the back are being built. We're interested in this because we can now think about problems which have dynamic obstacles, right, or the other cars, adversarial and cooperative behavior, and just multi-agent systems in general. We have some preliminary results where we have like multiple cars on the track. You can notice that if you want to do this with vision, which we are currently not, your lens will get mud on it from the car in front. So that's something you have to be robust to. We're interested in some interesting problems relating to sim to real. So can we use a simulator in order to actually train policies? Does this help at all? Can we build our own models of our tracks, which we have not done yet? Requires some time, but we're evaluating AirSim for doing a bunch of kind of sim to real type experiments. And then just to wrap up, I think terrestrial agility and racing is a great vehicle for studying AI. These types of aggressive maneuvering that we're trying to do provides an opening for machine learning when interactions become hard to analytically characterize. I think that's one of the major areas where machine learning can help in robotics. Reinforcement learning is an important framework for understanding robotics problems, but generally it's too hard. We want to do things to try to make those problems a little bit easier. Imitation learning is maybe a good alternative, and the expert doesn't have to be human. It can be any sort of algorithm that I can use. If you want to learn more, we have a number of recent papers on all of this sort of stuff. And we're kind of getting more into combining reinforcement learning and imitation learning, which we think is pretty promising. And then I have a bunch of other interests as well. So better ways of learning dynamics models, including recurrent neural networks. We're doing some cool stuff with quantum dynamical systems and graphical models. And in general, we've been doing a lot of work in robotics and inference. So this is just from the past couple of years in our group. So there's like a huge area of the lab, which I didn't really talk about today. I want to thank my awesome interdisciplinary team of grad students. These are robotics PhD students at Georgia Tech. Some of them are electrical engineering, computing, aerospace engineering. They've been working together to produce a lot of the work that you saw today. So thanks.
Okay, so we're slightly over time, so if someone needs to leave, feel free to leave, but we'll take some questions.
What is the application or motivation of research since the objective is run as fast as possible?
So I think it depends on what you're trying to do. So in general, I'm interested in artificial intelligence, machine learning control, and problems at the intersection. This particular application, we wanted to choose something which was where we have sensing, adaptation, control, if these are part of the problem. We also wanted to choose a problem that car companies are not necessarily looking directly at, which is trying to go kind of as fast as possible off-road. In terms of funding and like who thinks this is interesting, Army thinks it's pretty interesting to get from point A to point B over various terrain as fast as possible. So you can imagine that there's some scenarios there. But in general, I think that these type of vehicles are a good way of starting to try to understand terrestrial agility, just like how do I get cars or other vehicles which are really dynamic, how do I get them to perform well, where perform well generally means solve hard tasks like racing or trying to catch things or whatever. So I think this is kind of a start towards trying to solve some of those types of problems.
Question.
Yeah. Yeah.
You talked about using vision,
Yeah.
but have you considered using other types of sensors, like, I don't know, ultrasound or something? Something that occurred to me is that when you're going around the track so many times, you're actually leaving a path, and that vision might pick up on that path that you're moving and ignore a lot of other things.
Yeah, that's pretty interesting. So we haven't looked, we actually do have LiDAR that we can put on the vehicles, and we have not been using those so far. So there is definitely the opportunity to look at other types of sensors. With respect to what the car is actually looking at, what features it's using in order to navigate, we have done some work on looking at this. It uses a few things. So first of all, the car is basically using the inner edge of the track in order to decide how to turn. And then the second thing is it's often looking at features of objects in the background. So we think that this kind of tells us a few things. The features in the background are telling us something about the car's location on the track, which might bias it to take certain actions. The inner edge of the track obviously has to do with like what should my heading angle be. That also turns out, I don't put much faith in this sort of thing, but it turns out that these are, that sort of feature is what race car drivers use as well. You always are kind of trying to aim kind of diagonally towards that inner edge and keep that as something that you're sort of steering towards. So all of that just kind of makes sense. We haven't seen it picking up on like a track that it's left in the past, although that is a pretty interesting idea. So that would be pretty cool if it was doing that. Yeah, so that's our experience so far.
Okay, thank you.
Yeah, thanks. Yeah.
Okay, let's do one more question.
Okay.
So I previously asked you a question regarding the order of magnitude of trajectories. You said around 1600 to 2000. Considering your current track conditions, do you think this model will be able to scale well to real world conditions like army applications, etc.? The reason I ask this is Newtonomy is also following a similar generative approach where they create trajectories first, which are in the order of magnitudes of 100,000 as said by their CTO, and then they prune all the strategies using the country's driving rules. Okay. And then after pruning also it comes down to 16,000. Okay. So will this model be able to, because you're essentially averaging it, it's very costly.
Wait. So in this, okay. So in this case, the trajectories we're talking about. So I'm not sure exactly what Newtonomy is doing, but we're talking about basically generating trajectories using a dynamics model, and we're generating several thousand trajectories, and we're doing this multiple times per second. Your ability to generate more or less trajectories just is literally like a function of your onboard computation. The second thing is these trajectories, since they are a function of the dynamics, you can imagine scenarios where you have different dynamics models based on different surfaces or different situations. In that case, you just need to kind of switch between the dynamics models, and those whatever model you have will generate the appropriate trajectory. So I'm not sure precisely how it relates again to what autonomy's doing, but maybe that gives a little bit of an idea of more of what we're doing.
The question was more about whether you will be able to scale when a lot of conditions come. This model will be able to scale when a lot of such conditions come in. More parameters.
Yeah, so it's an interesting question. I mean, I think again that's mostly there are really interesting research questions about how can you adapt and how many different what variability of terrain can this robot deal with. I don't know the answer to those questions. I think in general, many of the things that you're talking about, like it may just be a function of how much processing power we have like on board. So if we can kind of keep a lot of models in memory and use them whenever we need to and figure out how to switch between them and stuff like that, then I don't see why we wouldn't be able to do that with the techniques that I'm talking about here. The other thing just to note is that this is talking about how do I actually control the vehicle when it's reasoning about somewhere in like the 2-second range of what's in front of it. So you can imagine in real world applications, you also want to be thinking about longer term longer term plans, and there's a number of other things which make it harder, including like other agents and things like this. My kind of interests are along the lines of combining ideas from machine learning and controls and thinking about just controlling these very dynamic vehicles. I'm also interested in planning and stuff like that, although it's usually with manipulators and mobile manipulators and in different environments like home environments and things like this. I know less about kind of like the overall picture for how do you design an autonomous car and this sort of thing. I will also mention though that using imitation learning from real world data is being used by several car companies, although I can't really say more than that. Yeah.
Okay. Thanks.